So our first speaker, Emily Williams, is from MIT. She's in the field of computational science and engineering under the advisement of David Dormefall there, and her practicums with PNNL. So let's welcome Emily, and we'll learn about generative modeling.
Yeah, thanks for the introduction. I'm Emily. I'm currently a postdoctoral fellow at the Odin Institute, but today I'll talk about some stuff I did during my PhD on generative modeling for multiscale chaotic systems. So my degree was in computational science and engineering. Computational science provides this unifying framework for researchers and practitioners to understand, predict, and assess complex physical systems. Oftentimes these systems are governed by partial differential equations, or PDEs. So on the right, what I'm showing is this computational science workflow. Oftentimes we're motivated by some real-world physical application that we model mathematically using governing equations. We discretize these equations numerically, and then we simulate them. A lot of times this can be using high-performance computing clusters. So for a lot of engineering and scientific applications, full-scale iterative experimentation can be way too expensive, impractical, or unsafe. So this is applications like the NASA X-59 supersonic aircraft, hurricanes and weather phenomena where test experimentation is impossible, and even rocket launches and satellite launches where one launch can be multiple billions of dollars. So the goal of CSE is to model and predict these systems. So a motivating example from my PhD is turbulent flow, which is present in many engineering and scientific applications. So on the right, what I'm showing is the supersonic flow around this NASA X-59 aircraft that I mentioned. But turbulent flow is everywhere. It's in earth science applications like atmospheric dynamics and weather phenomena, biofluids and biological systems like red blood flow through heart valves and artificial swimmers, astrophysical applications like gas planets, and environmental and civil engineering like flow past wind turbines. So discretizations of systems like these that involve turbulent flow contain way too many degrees of freedom to simulate accurately given limited computational resources. So there's a growing need for developing these reduced order models, or ROMs, that reduce these prohibitively large systems to a more computationally feasible set of degrees of freedom. Large eddy simulation, or LES, is one framework that has demonstrated capabilities in modeling chaotic flow at a more affordable computational cost. LES and similar frameworks involve the filtering of the Navier-Stokes equations, which introduces these subgrid scale terms that represent the effects of the unresolved dynamics on the degrees of freedom which are kept, and these must be modeled. So there's a lot of ongoing work, especially in the climate world and ocean modeling, that motivates the use of stochastic subgrid scale models for chaotic dynamics. Stochastic differential equations are used in modeling phenomena that appear to vary randomly or chaotically, so they could be a good fit for turbulence modeling. So the objective from my PhD was to improve the accuracy and stability of numerical methods for models of chaotic systems. Stochastic closure subgrid scale approaches can more accurately represent the complex multiscale interactions between the scales, and a lot of statistical closure strategies like generative modeling for efficient reduced order modeling in simulating turbulent applications at larger scales is a very open and growing area of research. Traditional deterministic closure models have also been shown to struggle with excessive dissipation or numerical instability, especially for large-scale applications. So there's a lot of ongoing work motivating the use of stochastic models for stability problems. So we can consider these results using the chaotic ordinary differential equation, the Lorentz-63 system, to talk through some of these ideas. So what we did here was we ran a fine scale trajectory, X, which I'm showing in blue on the right, and we applied this box filter, a filter with delta, to separate out the coarse scale or resolved variables, which I'm showing in orange here. And we can compute the fine scale fluctuations directly as the fine scale states without the resolved scales, and those are in gray here. So we can see when we apply this filter, we are filtering out these higher, can't see because I'm shaking, we're filtering out these higher frequency peaks, and that's what we want to model. So if we apply this filter then to the system for the dynamics, this x dx dt x dot is f of x, we can write this equation for the coarse scale dynamics here, where we have this Markovian term and this subgrid scale term, which is a function of the resolved scales and the fine scale states. So this subgrid scale term are the filtered dynamics without the dynamics of the filtered states. And in practice, we don't have access to these fine scale states, which is why we require a subgrid scale model, which we choose to do so stochastically. So here I'm writing the stochastic parameterization with multiplicative noise, this tau SGS, which here you'll notice it's a function of the resolved scales, and this C, which denotes the randomness. So we have this drift term lambda and diffusion gamma, and this is what we're using to model these subgrid effects. So here are two trajectories. In both of these, I'm showing the true filtered states in blue. On the left is with no subgrid scale parameterization, so just this Markovian dynamics alone, and on the right is with the subgrid scale model. So you can see visually that we appear to follow the true underlying scales with our stochastic subgrid scale model. We can compute this Wasserstein distance to actually measure this difference. The smaller the measure, the closer the distributions are to each other. And so we see here when we project onto the XYZ, we get about a 10 times reduction, which is good. So stochastic modeling of these motions does improve the representation and regime behavior for these chaotic systems. And we can extend this approach to chaotic partial differential equations. So now we have this PDE, this chaotic PDE, the Kuramoto-Sivashinsky equation, which changes in space and time. So I've written it here. It has nonlinear advection, diffusion, and dissipation effects. And we can apply a box filter in space and time now to write out the subgrid scale term, which again are the filter dynamics without the dynamics of the filtered states. And so here with PDs, we're interested in developing local subgrid scale models. So what this means is at each location I on the X point in the computational grid, we sample our subgrid scale term from a learned probabilistic distribution through a stochastic integration process. So what I mean by local is this learned distribution, this piece of data, is dependent or conditioned on the points that are around us in the finite difference stencil. So that's what I've drawn here. This is the computational grid with X along the bottom and time increasing upwards. So for example, with a fourth order finite difference scheme, we're conditioning on the point that we're at, the 3 to the left, and the 3 to the right. And this is critical, especially when we scale up to higher dimensional systems, because you can't always condition on all of the points in the spatial field at each time step. So here are the results for a case where the Markovian dynamics actually become unstable. So on the left, I'm showing the true filtered spatiotemporal field with X along the bottom, time increasing upwards. And then on the right is one realization using our stochastic generative subgrid scale model. And this involves a tuning parameter, this noise constant, sigma sub gamma, which we're setting as 1.4. And the way we can assess how accurate our model is by computing this frequency of an extreme event. This is common in climate science applications. So we set some S bar extreme, which is some extreme threshold. We set it as 9 for this case. And what we want to do is see everywhere in the field where we actually exceed the value of this threshold. So for the true filtered field, that's 2.4%. And with this realization using the generative model, we're at 2.7%. We can also see that our model is statistically accurate and stable across the entire temporal regime. So here I'm plotting the L2 norm over time. The true field is in black, the generative is in blue, and you can see that they're pretty close and it's stable across the entire regime, versus the Markovian dynamics alone in orange actually becomes unstable right away. Lastly, we can look at the energy spectrum. So this gives us a measure of the wave number content for each spatiotemporal field. Basically, it shows us how well the different spatial scales are represented. So in the black dotted line, this is the true field, and then the generative is in blue. We can see pretty accurate agreement along this decay and peak with some improvement that we could do for the lower order wave numbers. So the generative model is stable and statistically accurate, critically in this case where the Markovian model fails. And so, like I said, improvement in preserving the wave number content across the different spatial scales is something that we want to do. So my PhD work kind of covered a lot of ground that can be situated nicely in this computational science workflow that I referenced. Today, I only talked about a few things having to do with this red box, so these coarse-grained closure models using generative modeling. But in collaboration with PNNL, we also built these projection-based reduced order models using physics-informed spectral methods. Did it just get louder? It's fine. And then also, I looked at ideas in stability where we developed these generative stabilizations for linearized chaotic dynamics. So the results of what I did motivate future work in investigating more principled stochastic closure models, which are accurate and stable, critically for scalable deployment in exciting scientific applications. So my work kind of went up to 1D chaotic PDEs and demonstrated deployment resulting in improved accuracy at fixed cost or minimally added cost. But in general, it's important that the models that we develop integrate with scalable infrastructure. So this includes being able to be used with existing legacy codes that use traditional numerical methods, and extensions to higher dimensional flows, like I mentioned, with complex geometries. So this would demonstrate feasible application for engineering systems. So a natural next question that's kind of motivating what I'm doing for my postdoc is you might ask, what do we do if we don't know the equations of motion for the underlying dynamics? So for a lot of problems that I'm interested in, or you might be too, is in nature, engineering, and even society, where we don't always have a complete mathematical model which govern the mechanisms of the system behavior. So my PhD kind of covered this first setup where we know the physics, we have some missing dynamics, and we learn these closure models to account for what we're missing. In a similar kind of theme, there's this setup where we don't know the complete physics, so unknown or partially known physics, but we might have a lot of experimental data or high fidelity simulation data, and we can use those to build these digital twin models that can update in real time. So this has a lot of applications in structural engineering, aerospace engineering, and even educational applications. So like modeling student trajectories so advisors can better kind of have these just-in-time interventions to help students reach graduation. This is something that I'm really interested in too. So like modeling transfer pathways from community colleges. So how can we best set up students for success? The CSGF is one example of an intervention that kind of helped me reach graduation. So, like the engineering stuff too, obviously. But so as a postdoc, I'm interested in kind of extending some of these things I did during my PhD to more data-driven applications where we can really make an impact with things. Obviously, like I said, none of this would have been possible without the CSGF. I think I would have lasted a couple months in grad school without the CSGF. So anyone could have done this generative AI stuff for engineering. Everyone's doing it. Anyone could have done this. But obviously, I'm grateful to the CSGF for kind of investing in me as a researcher to get here. So that includes the other fellows in this room and alumni, and like MIT also, and PNNL and my practicum supervisors who eventually kind of became co-advisors on my committee, which I'm very grateful for their support. And then UT Austin, I mentioned I started there last month, so I wouldn't have gotten that offer without kind of my experience with the national labs and what I did through CSGF. So yeah, that's what I mean when I say none of this would really have happened. But that's it, so I'll wrap up 50 seconds early.